Welcome, class. Today we're actually going to talk about section 2.7, nonlinear inequalities. But before we do that, we're going to have a review of finding zeros, the methods we can find zeros with, and then the discussion of when you want the test. So the test normally is scheduled for it would be this Wednesday. Now, the realistic thing is you could still do this. This is very doable. Like this section is gonna not have as many word problems again as previous years would have, and it's gonna have this information basically pretty well laid out. The question is, do you want to do it this Wednesday, or we could do it Friday? If we do it Friday, we won't do. We would have a free day, semi-free day for chapter 3. So if we do Friday, we won't have that free day. We will just go straight from, chapter 3. We'll just go straight into the test. So it's your decision, but just know that that's the first minute of this video. Okay. So we're going to cover nonlinear inequalities, basically meaning when we're going to have how do you graph what solutions will happen with nonlinear inequalities. So key numbers are going to be the zeros, any wholes, any asymptotes. So key numbers are going to be zeros, wholes, or asymptotes. I don't know why it doesn't say this in the book. Sorry about that. Let's close up. But anyway, that's the key numbers. Okay, so that's key numbers. Test intervals, which is going to be what we're going to discuss, and it's the intervals given by our key numbers. Okay, so many of you are going to need to learn interval notation, but before we do that, we need to review briefly, very briefly, finding zeros. So remember when we covered, so zeros of rational functions are going to be our x-intercepts. That's going to be, so for polynomials, there's the rational, this is the rational root test. That's what I'm used to calling it. Rational zero test. There's Descartes, rule of signs, and then there's complex root zero rules. Okay. Then for rational functions, you set the numerator 0 and solve, and then the denominator equal to 0 and solve. Okay, that's going to give us, sorry, it's not. Okay. Okay. Those are going to be our approaches for this. I am going to upload the full filled out one. So asymptotes are going to be what we need to find. So vertical asymptote is going to be denominator equal 0, and or this could be a whole. A whole is not simplified. Okay. And then horizontal, if the degree of top is less than degree of bottom, denominator, then HA equals 0, degree of top equals degree of bottom denominator, and then HA equals fraction with leading coefficients. We'll talk about this. And then finally, if degree of top is greater than degree of bottom by 1, then it's going to be it's going to be a slant asymptote. And if it's top is greater than bottom by more than 1, then no HA. Okay, that's our rules. Okay, so make sure you wrote them down. These are all the rules. Okay, writing intervals. I'm not going to write on this notes. I'm going to just write on the board. So, an interval has either it's open parentheses, open, or closed. Closed means our function is continuous and at that point. You can think of it as saying the function actually has a value. Open is where there is no value. I'll explain what that means. Okay, so closed is going to be important, and open is going to be important. So open, let's look at an example. So let's say we have y equals 1 over x, okay? Now, is this function go to infinity and negative infinity? Yes. So by nature, we always start at negative infinity, lower to higher, but we have a vertical asymptote at x equals 0, right? Because x can't equal 0. So our first break in our function is going to be this, okay? 0. It's going to be open because our function never reaches that point, okay? Just as infinity, it doesn't reach infinity. That's not a specific point. Okay, now, key idea. When we're writing this, let's see what they do in the book. Oh, they just have commas. Do they do anything else? No, I guess they, well, okay. So then our next part of the function is the right side, which is going to start at 0. And then again, our x is going to approach infinity. Okay, these are both open, okay? We have no closed brackets on this one, okay? Now let's look at a function that will have closed brackets, so you have the context, okay? A good example of a closed bracket is actually the function f of x equals the square root of x. Now this function has a downward limit, okay? And that's 0. We can plug in 0, but anything below 0 can't work. So this would be a closed bracket. And then can x approach something? Yes, it can approach infinity. It has no upper bound, okay? Again, this would be open because we never reach infinity, okay? There's no value for x. If you plug in infinity, we don't know what the answer is, actually. Because infinity's range in size, okay? Okay, so that's closed and open. And just put commas between them right now. We'll talk about whether you put U, the union, or something like that. So I'll talk about that as we go. That's the basics, okay? So that's how we write intervals. Now let's go to finding test intervals for a polynomial. It's going to be our next video. So